Okay, so where were we last time? So if I would summarize sort of one of the main messages of the last talk, it would be the following. So we had the Coulomb branch of the moduli space of this quantum field theory, theory X, compactified on a Riemann surface. Let me use C0 now for the zero area limit of that Riemann surface. Last time I used C comma 0, which turned out to be cumbersome. Across a circle. The circle is of radius r. So we talked about this Coulomb branch, and we also talked about the Coulomb branch of the moduli space of the four-dimensional theory lying above. So again, I'll take it to be the zero area limit. So this Coulomb branch was the Hitchin integrable system. So let me just call it M now. It's really M of C and G. And as we discussed in the discussion section, it's possible to enrich this thing by putting punctures, by putting defects on C, and then this would be the Hitchin integrable system with singularities. That's using these four-dimensional defects of the theory X. So this one gives you Hitchin's integrable system, and this one gives you the Hitchin base, so the base of Hitchin integrable system. So I'll call that B. So the picture was, here's B. We have some special points, or some special divisors, but I always draw it one-dimensional so they just look like points. Some divisors on B where the physics is complicated, or potentially complicated, but away from these points. So the physics here, the low energy physics here, was governed strictly by abelian n equals to super Yang-Mills. So we're going to use this fact today. So there's the Hitchin base, and then Hitchin integrable system, of course, is fibered over that base. So the fiber over these nice points, where the physics is just governed by abelian n equals to super Yang-Mills, the corresponding fiber is just a compact torus, and then above these bad points, the fiber may be something more complicated, something singular. Okay. So when we talked in the discussion session also a little bit about why you get a torus as opposed to something else. But I want to say something a little more fundamental, which is, you might ask, why is there a map at all? So why is there a map from M to B? From this kind of abstract point of view of field theory, right? Okay, so why is there a map from M to B? Well, let's say it like this. So as essentially all the other speakers have done, let's think a little bit about the supersymmetrically protected local operators in this theory. So let's let R be the ring of chiral. So chiral means that they're preserved under some particular half of the supersymmetry. Local operators in this four-dimensional theory. So the four-dimensional theory, which is xg of C0. Okay, now first of all, these operators, as other people have said, these chiral operators form a nice ring. So you can just define the product of two operators to be just obtained by taking the two operators and bringing them very close together so that you get another local operator. So there's a natural ring structure on the space of chiral operators. And moreover, so taking the vacuum expectation values, so taking the one-point correlation functions, if you like, one-point functions, one-point functions, say, so given any operator, I can consider the one-point function, the correlation function where I just insert that operator. I can insert it at any point, but it won't matter what point I what point I take. But what does matter is in which vacuum I evaluate it. So I evaluate the one-point function in some particular vacuum, call that vacuum B. That gives a function. So I'll call them f sub O. So for each operator O, I get a function, fo on B. And in fact, in this theory, as in many theories, although I don't know a general reason for it, in fact, B is just the spec of the ring of local operators. So here we see at least that the local operators are realized as functions on this space. But in fact, B is just the spec of that ring. So I mean, you can prove it sort of by hand in this particular example easily enough using the description of the local operators that I already told you in 6 dimensions. Anyway, so it's a true fact that B is the spec of this ring. Now, in that language, how do we understand that M is fibered over B? It's simply the fact that if you have a local operator in the 4-dimensional theory, then when you compactify, that also gives you a local operator in the 3-dimensional theory.
Does this also give you for free that these guys pass off compute?
That they what?
Pass off compute to each other?
Probably yes.
You think about their OPEs, right?
Yes.
Different points in the circle, they have no singularities, so that's the causal structure.
Okay, yes. So local operators in xg of c also give local operators in xg of c cross a circle, which moreover have the same OPEs. The OPE is a completely local thing. It doesn't care whether the theory is put on some big circle or not. And so we get a map. So we have functions corresponding to all those local operators. That gives you a map from M to spec of R. In other words, a map from M to B. And that is exactly the. That's literally this map. That's Hitchin's integrable system. So the fact that this space. So the point is, if you think of it just as a sort of 3-dimensional field theory, you don't detect the fact that the space is actually an integrable system like this. So the first bit of extra structure that you get by realizing that this Rosansky-Witten model actually came from 4 dimensions, the first little bit of extra structure that you get is the structure of this integrable system. All right. Okay. That's good, but of course that's a structure that we knew about before. So let's see what else can we get. So by the way, one thing to say about this map, I told you that these are chiral operators. They're protected by some kind of supersymmetry, and what that's going to correspond to in the language of these maps on M is that they should be holomorphic maps. So it's holomorphic. That I get a map from M to the spec of that same ring rather than to. So the ring is literally the same ring. We're just realizing that ring now inside the space of functions on M instead of the space of functions on B. You're kind of just pulling back the functions from the base. So it's important that those functions satisfy the same relations. So this map is supposed to be holomorphic. The thing being chiral says that this map is holomorphic. Now when I say holomorphic, this M is a hyperkähler space, right, as you emphasized. So it's holomorphic in one of the complex structures on M. In the complex structure, I'll call it J0. So remember, we had this family of complex structures, J zeta, zeta lying in CP1. And this is a complex structure which evidently is somehow distinguished. It's the one which is coming from the reduction from 4 dimensions. And in the abstract language of the Hitchin system, it's the one for which the Hitchin system is realized as the moduli of Higgs bundles, as opposed to being the moduli of local systems. So this map is holomorphic in one particular complex structure. Okay.
So we have this compactification in S1, and we see that moduli space of vacua projects. Is it typical that, like for compactification, somewhere moduli space of vacua is surjectively projected in corresponding direction?
I mean, this mechanism that I just described here looks like a pretty general mechanism, right? So yeah, I think that's going to happen.
Well, always got on map. There's no reason this map. There's no reason yet this map is going to have any good properties, right? There's no reason. We haven't. At least I haven't heard a reason why this map should be subjective or.
Yeah, well, at least subjectivity isn't kind of clear.
So right. So the question is, could it be that the vacua of the could it be that after you compactify the theory, it loses a lot of its vacua for some reason? That generates a superpotential or something like that. It's hard for me to believe that that would happen on compactification on a circle.
I mean, there's a natural section for this map. The Hitchin section you can also construct using the quantum field theory. And so, yeah, so it's not, so it's subjective.
I mean, but that statement depends on the fact that this compactification was done in a way which preserves some supersymmetry. If I did a very general kind of compactification, it could indeed happen that the supersymmetry is broken, it generates a superpotential, and all the vacua get wiped out. So I mean, so no, I mean, as usual, I hesitate to make any very general claim about what happens in a general quantum field theory. In this particular quantum field theory, it happens like this.
What is this section that they do this?
The Hitchin section, just the Hitchin 0 section.
Yeah, but have you seen that from the QMT?
How do you construct it directly in?
Presumably something like the vacua that happens to have some sort of particular behavior in this circle.
Yeah, I mean, it's the ones. I mean, one way you can say it is that you have sort of zero holonomy for the gauge fields around a circle. So it's preserving a parity symmetry that's otherwise broken. That's probably one way to say it. Yeah. Yeah, but let me go on. Okay, so we have this much, and now. So I want to get some kind of new structure on the Hitchin space. And for starters, I would like to have something which is able to detect the whole Hitchin space. If I only have these operators, I literally can only detect the Hitchin base. I don't detect the torus fibers at all. So how to study all of them, in particular, how to even detect all of them. OK, so we're going to need more operators. OK, unfortunately, we have more operators. So for example, let's do the following. Let's take a supersymmetric line defect, line operator. I use the words line operator and line defect largely interchangeably. So take a supersymmetric line operator from the four-dimensional theory. Let's see. Let's call it L of zeta in the theory, in the four-dimensional theory, xg of C0. Why do I call it L of zeta? Because these supersymmetric line operators, so as it'll turn out, the supersymmetric line operators typically come in families. This parameter zeta is parametrizing which supercharges exactly are preserved. So the zeta is lying in CP1, and you should think of that CP1 as being the same CP1 that appeared here. But for the moment, it's just parametrizing choices of supersymmetry. So let's take one of these supersymmetric line operators, depending on a parameter, and let's wrap it around the circle. OK, so in this compactified setup where I have the, I've taken the four-dimensional theory and put it on a circle, I could take my line defect, supersymmetric line defect, and put it on a circle. And I could compute now, compute the partition function with this thing inserted, or compute the correlation function. It's again a kind of one-point function, but now it's a one-point function of this line defect wrapped around the circle. So this gives, sorry, I should write it higher. So what does that give me? This gives now a function which I'll call f sub L of zeta. So it's a function depending on my line operator. Again, on the Hitchin integrable system, a function to C, defined by FL of zeta in a particular vacuum, is this one-point function, or one circle function. It's a correlation function with one operator inserted around a circle, computed in a particular vacuum, whatever vacuum you like. Okay, so for example, so what are these functions? Okay, so I say these are some more functions on Hitchin's iterable system. What are these functions? So for example,
does this discussion have anything to do at all with class S? Would the same thing happen if I took any four-dimensional theory? Do I always expect the sort of iterable system structure to arise in this way?
yes. Exactly up to this point, I've said nothing that was special to class S. In the next moment, I'm about to say something that depends on class S. So for example, so suppose we're given the data of P, a loop on C. So now I'm going to use class S. So I'm going to use this internal curve, which up till now I didn't use. A parameter zeta in C star, and a representation R of the group, which we have in the background all along. Then, as I told you, I think in the second lecture, there's a corresponding line operator in the four-dimensional theory, LPR of zeta. In this theory, xg of C0. So I'll remind you the picture that went with that, right? Well, okay. The picture that went with that is just a picture of the curve where we've wrapped something around our loop. So here's our loop P. Remember that in the six-dimensional theory, we had a potential sort of surface operator. Now what we're doing is we're taking that surface and wrapping one loop of it around this loop here. That leaves one dimension left over, and so that's why that gives us a line operator in the four-dimensional theory. So don't confuse this line with this line. It's rather that we're making a single surface, which is the product of those two lines. Anyway, so we get a line operator. So
This is some sort of polynomial.
yeah, great. So what was the meaning of zeta in terms of right? So in the six-dimensional theory, I told you that the line operators depended on a parameter, right? The parameter was some vector in some it was like a vector in R5. Now we've split that R5 into R3 plus the cotangent, and this zeta is in fact giving you more or less the cotangent direction. Okay, so there was a parameter there, and that parameter has survived into here. We'll see in just a second how it enters into the answer. Yeah. So then, what is the function going to be? So.
Don't erase that thing yet. I wanted to ask a question.
Okay.
So you erased what I was about to ask a question. Why did you just erase the CP1 but you have a C cross there?
Well, okay, great. So, oh, did I write CP1 here? I should have written C star here. So in fact, the line, yeah. So the line defects are always supersymmetric with respect to only a C star out of the CP1. You don't get line defects corresponding to z equals 0 or z equals infinity. Yeah, that has to do with the fact that the supersymmetries under which you're asking the thing to be invariant, if zeta is not 0, they square to a translation, so you have a translation along the line defect. If zeta is 0, that in fact corresponds to in that case, the supersymmetry squared is 0. So you don't have to have a translation. You can have a local operator, and those are the operators that we talked about before. Yeah. That's right. So this is going to be only for zeta and C star. Well, that'll look more natural in about 1 second. So what is the function in that case? So now it's f, L depending on the path P and the representation R and zeta, and it's going to be a function on the Hitchin space. So what is it? Well, okay, what's M? So remember what M is. M is Hitchin's iterable system, so a typical point of M is given by a connection in a Higgs field obeying Hitchin equations. So given the connection in the Higgs field, we make the following thing. So this function is going to be a holonomy. It is going to be the holonomy of something around that loop. What is it the holonomy of? So it's the trace of the holonomy around the loop P of a connection. So trace in representation R, the holonomy around P of connection nabla of zeta, where nabla of zeta is this particular thing. So a solution of Hitchin equations is a unitary connection plus a Higgs field. You take the unitary connection and add to it some multiples of the Higgs field in this particular combination. This is a nice formula. So it's a sort of cool fact about Hitchin's equations that you can think of Hitchin equations just as the statement that this connection is a flat connection. And when I say it's flat, I mean it's flat for every value of zeta. That imposes two equations, and those equations are exactly Hitchin equations. So this is a flat connection, but of course you see it only makes sense for zeta and C star. But as zeta goes to 0, this thing is kind of becoming singular. As zeta goes to infinity, it's becoming singular. Okay.
Say like 2 words about how you make that calculation.
How you make what calculation?
The fact that this is what the line operator does.
Oh, so that comes from this 5-dimensional Yang-Mills. So I told you, one of the things I told you, which was kind of one of my pseudo-axioms about the 6-dimensional theory, was that if you take a surface operator, the surface operator of the 6-dimensional theory, and compactify it on a circle, it becomes the Wilson line of 5-dimensional Yang-Mills. The Wilson line of 5-dimensional Yang-Mills is exactly a thing which computes the holonomy.
And we already decided we're okay with compactifying first last 1 and then on sigma instead of first on sigma and then last 1.
That's right, that's right. So we're blaming this sort of bizarre fact that everything is independent of the scale of the Riemann surface to allow us to make that kind of interchange. So I'm freely using the 5-dimensional Yang-Mills perspective in order to get this concrete formula, absolutely. Right, so it's ultimately the power of having this circle in the story, the fact that I'm trying to describe a thing here. Okay, very good. So that's a function. So that's a perfectly good function. It's a holomorphic function. So another cool thing about the Hitchin space. So this function is a holomorphic function on the Hitchin space, thought of as a space. So it's a hyperkähler space that has the CP1 worth of complex structures. In complex structure zeta, this function is holomorphic. Yeah.
And so the radius of the S1 is some finite value, and
Sorry.
okay.
Did that help?
So keeping that finite is
Yes.
kind of what is allowing you to rewrite this as Hitchin equation.
No, keeping it finite is not particularly what's. No, I mean morally the limit in which this would naively work is the limit in which we study energies much lower than the scale 1 over r. So morally speaking, it's keeping it small, which would be helping us. Yes. Okay. So that's a holomorphic function. So what do I want to say about it? So first of all. So for example, let's be really concrete. Let's take the Lie algebra to be just A1. Then these functions. So we have these functions f, p, r on the moduli space. So as we let the loop p and the representation r vary, these give us actually a linear basis for the ring of functions, for the ring of holomorphic functions, for the algebra of holomorphic functions. Linear basis for the algebra of holomorphic functions. On this moduli space. And this algebra has another name. It's sometimes called the skein algebra. I think I'm saying that correctly.
Is this fact false for G not A1, or you just don't know if it's true? Or?
Yeah, for G not equal to A1, it's kind of a trickier story. So there's a question of whether you need to. I think that you need to include, in addition, some of these spin network kind of things. So where you don't just take a loop, but you take like. You take something like this with 3 representations and intertwiners at the various places. But then if you take all such things, then you don't get a basis. You get something that's over-complete. I don't think it's well understood, certainly not by me, exactly what would be the sort of good basis to take in that situation. You might think that the theory X perspective would somehow help you to understand that, and I'm sympathetic to that, but I haven't seen a precise. There's been some work done. I mean, for example, by Dan Shi and recently by Matt Bullimore, but I don't think it's yet a totally complete story. Yeah.
Can you associate something to a curve that terminates at a function?
Yeah. Okay. So if you have regular singularities, then you don't do that. But if you have irregular singularities, so these singularities where several things have collided, then you do also include you do also allow some paths that run into the punctures. But you can understand that again from taking the limit. So The idea is if you have a path that goes between two punctures and you collide those two punctures, then it kind of pinches the thing off. And so yeah, it turns out to be natural to include things that also end on the punctures. Only in the case of irregular singularity.
Are we only discussing the case when there's at least one puncture?
We're not only discussing the case where there's at least one puncture. Although I, secretly in my head, I do usually think mostly about that case. But no, in principle, we're not.
I don't understand the algebra of holomorphic functions on M, because like all these 4 by 5s, the holomorphic functions are just going to be constant.
Holomorphic functions in complex structure zeta. Right, this is the most, sorry. Right, so remember, this is a hyperkähler space. It has one complex structure in which it has not enough holomorphic functions. That's the one in which it's fibered over the base. So those were the functions that we first found. Then the question was how to get more functions. And the trick was that taking these line defects from here gave us a natural basis of holomorphic functions in the other complex structure. That's right.
So zeta equals 0 is the Hitchin system?
Zeta equals 0 is the Hitchin system. That's the one which doesn't have enough holomorphic functions. Here the thing is, I think, just affine, so it's fine. OK, great. So the first sort of qualitative comment is that by considering these line defects, first of all, we got more holomorphic functions, but maybe more important, we got somehow a distinguished set of them. We got this distinguished set of them corresponding naturally to taking loops, a preferred kind of linear basis for the algebra of holomorphic functions. Now, let me say something now a little bit vague and conjectural. So the actual line defects themselves, OK, so we heard a lot in the previous talks, particularly in Kevin's talk this morning, about line operators in n equals 2 theories. And here's a case where we're studying exactly supersymmetric line operators in an n equals 2 theory. So as Kevin and David both emphasized, it's natural to think that these things form a category. So I want to say indeed, so in the context of class S, what we see should be some kind of, so because of my personal incompetence, I just say some kind of categorification of the skein algebra. I just want to make the point that that's what appears naturally when you go up in one dimension. The thing is sort of automatically categorified. It seems that it should be automatically categorified. And if you ask what's the kind of geometric picture that would correspond to, so what is a morphism from a physicist's point of view? At least one way we could think of a morphism is simply that we have a line defect, say corresponding to path 1. We have a line defect corresponding to some other path, path 2. And the morphism would be a kind of local operator that lives only at the interface between these two things, that interpolates between one and the other. And what's the corresponding geometric picture? What is this morphism? Well, if you think of trying to construct it by wrapping the surface defect of the 2, 0 theory, what you would be led to guess is that it has something to do with making a cobordism between the two. So here's the path P1, here's the path P2, and here's a cobordism between the two, which corresponds to putting the surface defect on here. That corresponds to this morphism. So very naively speaking, that's the shape you might imagine such a categorification to take. OK. I don't want to say any more about it because I don't know anything about it. So maybe the other thing that's worth saying is that, so as Kevin and David also said, whatever this category is, it should be a monoidal category. It has a natural operation of tensor product, where we take two line defects and bring them very close together. Then if you look at that thing from far away, it now looks like a single line defect, which you might call LP1 tensor LP2. OK.
Can you clear up the actual way of this diagram?
Yes.
If you take sigma equals T2,
Yes.
then are those two last columns the same, or are they different?
If you take sigma equals T2, they're the same, but there are some unpleasant features. OK, so the question is, yeah, what if I do the class S theory where the surface is literally T2? What's going to happen in this case is that every Higgs bundle in that case is reducible. So what it means is that there's no sort of independent Coulomb branch. The Higgs branch is kind of sticking out of every point of the Coulomb branch. So you really have, from the point of view I've been saying, you just always have this mixed branch. And everything I've been saying has been about the situation where you just have a Coulomb branch. So for me, I think of those as being a little bit, I like to exclude that case in most of my internal thinking, although David likes to do exactly the opposite, I think. He likes to think of that as just literally a special case. If you do it in the correct derived way, it's no problem from his point of view. And I'm sure that that's a good point of view. OK. But I know that, but there is a funny thing. I mean, for example, right, there's some positivity stuff in the skein algebra which seems to fail in exactly that case. So OK. So what's my aim here? So I would like to actually compute these functions. So given a point V of m, the Hitchin moduli space, how to actually compute the functions attached to these loops, say. So I mean, of course, I told you that they're given by the traces of the holonomy of these connections. But nevertheless, suppose I want to compute it just as an actual function of zeta. What is that function? Well, how do we do it? Well, so I should say what the ground rules are. The ground rules are, suppose we're given. Yeah, let me make my life a little easier. Let's take this point V to be lying on the Hitchin real section that was just mentioned. So given V on the real section of the Hitchin fibration. So in that case, it's labeled by a point of the base, a point of the Hitchin base, just a point U. OK, so yeah, and I should say that the strategy that I'm about to describe is kind of cobbled together from various papers, joint work of mine with.
What is the section, Andy?
Sorry?
What is the section?
The real section?
Yeah.
It's the one corresponding to taking the spectral line bundle to be trivial.
Okay, so why is it the real section?
It's called the real section because, it corresponds to the solution of Hitchin equations which have a reality property. Let me not instantly say what it is. But yeah, it's just what you think is the zero. It's what you usually call the zero section, the Teichmuller component of Hitchin of the Hitchin moduli space. So I'm going to describe a strategy which is basically joint work with Davide Gaiotto and Greg Moore. As is actually, the stuff that I reviewed about theories of class S is also largely joint work with Davide Gaiotto and Greg Moore, as well as, of course, there's quite a lot of work just by Gaiotto himself. OK. So how am I going to actually compute these things? So the key idea is to use this idea that we understand very well the low energy physics of this theory. So let's try to find a low energy description. Of this line, the line defect. So what does it mean to find a low energy description? Well, I told you at some point that. So we think of this first in the four-dimensional language. This line operator is a line operator in four-dimensional physics. The four-dimensional quantum field theory that we're studying, we know what its low energy physics is. Its low energy physics is just, as I said, just a abelian gauge theory. So the question is, if you had a low energy description of this thing, what could it possibly be? It would have to be some line operator in abelian gauge theory. OK, so what are the line operators in abelian gauge theory? So in the abelian gauge theory, so there's some abelian gauge theory which describes the physics at this point of the Coulomb branch. You can classify all the line defects. And as it turns out, there's just one line defect for every possible electromagnetic charge. You can think of them as being supersymmetric versions of, for the electric charges, they're just supersymmetric versions of the Wilson line. And for the magnetic charges, it's supersymmetric version of the 't Hooft line. Or you can use electromagnetic duality to always make it electric. So the supersymmetric Wilson 't Hooft lines. But really, if you understand Wilson lines, it's enough. You don't really have to understand what a 't Hooft line is for this. So I won't write yet the formula. I won't write a formula for the line defect, but I'll just say. So there's one for every possible electromagnetic charge. So we had this lattice of electromagnetic charges. And we just get one line defect for every lattice vector. So simplest thing you could imagine. A lattice worth of them. Let me write so now we're interested in computing the vacuum expectation values, the one-point correlation functions of line defects wrapped around the circle. So suppose I take this line defect L gamma of zeta and wrap it around the circle, just in pure abelian gauge theory. What we would get, so that you pretty easily compute explicitly, it's just given by a formula like this. It's the exponential. It's like a complexification of a holonomy. So first there's the holonomy of the abelian gauge field, which I'll just write I theta gamma. So this is the holonomy of the U1 gauge fields. So if you like, these are the coordinates on the torus of the Hitchin fibration. So this is just like a Fourier mode along the torus of the Hitchin fibration. And now we kind of complexify it. So we add functions from the Hitchin base, which are these central charge functions that I mentioned last time, these functions z gamma and z bar gamma. Those are just holomorphic functions coming from the Hitchin base pulled back. OK, so some simple explicit formula, which of course has a horrible essential singularity as zeta goes to 0 or as zeta goes to infinity. And that's just the nature of things. Functions on the Hitchin space are just like that. They kind of have to, because there's not enough functions at zeta equals 0. So when zeta goes to 0, something horrible has to happen to the functions, and this is what happens. OK, so that's the story of the kind of line defects of this abelian gauge theory. That's the simple story. That's like our model.
Sorry.
Yeah.
The z gammas for the periods of some differential.
Yeah, that's right. That's right. So.
Can you told us how to build that differential, or?
Yeah. So let me remind you. So every point u of the Hitchin base, there was a corresponding sigma u, which was a k-fold branch cover, of the Riemann surface C, which sits inside the cotangent bundle. And because it's in the holomorphic cotangent bundle, it just has the Liouville one form.
Okay.
So z gamma is just the period over a cycle gamma. It's just the period over a cycle gamma of this lambda, what is it called, the Liouville one form.
Could you remind again what's k in this case?
K, sorry, that was for, yeah, thanks. This was for, this was in the case of the group AK minus 1. So only in this case I have such a simple explicit description of what this thing is. Yeah, so let me, in fact, I may often slip and tell you something which is valid only for AK minus 1.
So I understand. So
Yeah.
the point here is that it's easy to compute polynomials of abelian fields.
That's right. It's easy to compute them classically, and it's also easy to compute them even in the quantum theory. That's right. So this is the expectation value of that line defect, provided that you study a quantum field theory, which is literally just the abelian gauge theory. Everything is just free. It's completely simple. Yeah, and the idea is going to be to relate our complicated situation. Yeah, so I mean, morally speaking, what we're going to do is the following. We're going to make a passage from what do we have? We have some Riemann surface C with a loop on it, P, and we're going to compute the some tricky holonomy around this loop, the function that we defined before. But the way that we're going to get it, okay, well, this covering should be somehow more complicated looking. I don't know, it has more, it's branched and so on. The way that we're going to get it is to relate this thing down here to holonomies around loops on the spectral cover. That's going to be the idea, is the sort of reduction of everything to the spectral cover. But let me say more precisely what that's supposed to mean. So the picture is the following. Here's the claim. So in the theory, in this four-dimensional quantum field theory, xg of C0, for any, but now it's a little bit subtle maybe, for any generic choice of u and zeta, so u is a point of the Coulomb branch of the Hitchin base, zeta and C star, there exists a collection of integers. I'll write them like this, with this kind of funny omega with lines over it, depending on a bunch of stuff, depending on the loop that we consider on the base, depending on a loop that we consider up on the cover, depending on where we are in the Hitchin base, and depending on zeta. These are going to be numbers. Such that at low enough energies, so I want to describe this, I want to describe what this defect, this complicated defect, what it looks like when you look at it relative to the abelian theory, where everything is very simple. So it has to look kind of simple. And what it looks like, so the defect that we had, LPR of zeta, is described by, I guess I'll just write this wavy arrow, is described by a sum over possible charges, a sum of the line defects of the abelian theory weighted by these integers.
What does squiggly arrow mean?
Yeah, it means that, it means that if you flow into the infrared in the four-dimensional theory, it's a kind of physical question. It's, you have this defect in the ultraviolet. What does that defect look like when you look at it in the infrared? So in the infrared, it's some supersymmetric line defect. I take it back. If it has a good infrared description, and you'll see what I mean by that in just a second. If it has a good infrared description, that infrared description would have to be in terms of the line defects of the infrared theory. It would have to look like some combination of the line defects of the infrared theory. The supersymmetric ones, and I told you all the supersymmetric ones. So the only remaining question would be, with what coefficients do they occur? But you'll see what this means in correlation functions in just a second. Thank you. No. This is not the function. Sorry, this is not the function. This is the actual line defect. We're going to pass to Of course, this is going to imply a statement about the functions. But I want to emphasize that it really occurs at the level of this category. I mean, this is really something about how objects in this category are built out of simpler objects. Yes, so this is the dimension of a, so sure enough, this is the dimension of a Hilbert space. The way you understand that is look at the Hilbert space on both sides of this equation. So remark, indeed, so this integer, omega of p, r, gamma, u, and zeta, is a kind of graded dimension. It's a supersymmetric index. Graded dimension of so to be exact, it's the charge gamma part of the Hilbert space of the theory. So we take the theory, what is our theory called? Xg of C, a four-dimensional theory, with the defect P inserted. Sorry, with the defect L, P, comma R of zeta inserted. So what do I mean by the Hilbert space with the defect inserted? So the picture is, we have our 4-dimensional space. We put this defect here in 4-dimensional space, and then we're slicing it. To take the Hilbert space, you look at some 3-dimensional slice, right? So we're taking the Hilbert space on this 3-dimensional slice, but with the defect stuck in there at a point. That gives you some kind of modified Hilbert space depending on the defect. And now we're looking at the BPS states. We said what BPS is in the discussion session. Let me not try to say it again. Anyway, it is in fact some vector space attached to the defect. So that's exactly the way you're supposed to think about this. And the way that you see that equality is by taking the Hilbert space on this side, which gives you exactly that, and taking the Hilbert space on this side, where this defect you usually see has just one state. And so that gives you the equality.
If there's expectation values on both sides, that would be an example.
If I took the expectation values wrapped on the circle on both sides, then it'll still be an equality, but I have to be real careful what I mean by this. So yeah, so we'll come to that. Sorry? U should have been there. Did I drop it?
It doesn't occur in your description,
Yeah, because the whole thing, this quantum field theory. So remember, when we compute anything in this quantum field theory on a non-compact space, it's always a function of a choice of a vacuum. So here we're computing a thing on R4, and so I always have to choose a vacuum. So, but you're right. Here I should have said the theory in vacuum U. Absolutely right. And these numbers certainly depend on which vacuum you're in. They have a very non-trivial kind of jumping behavior. So that's critical. Yeah. So indeed.
I'm also just not totally sure I know what charge gamma is. Usually I think of charge as a number as opposed to something CSR.
No, gamma is a, yeah, so gamma is living in the lattice.
Oh, yeah, yes.
Right, right. So that's the lattice of electric and magnetic charges in this theory.
Yeah, it's a dual photon.
Oh, sorry, it's not the dual photon from the other talks. Yeah, that's right. That's right. So given this guy down here, we're relating it to a bunch of guys up here with some particular coefficients. Okay. So indeed, so this description, so I told you that there's going to be this description of what the line defect looks like, what it looks like in the infrared. And this description is supposed to break down at some real codimension 1 walls. A real codimension 1 locus. Let's call it L mu. That's the locus of, so it depends on the parameters u and zeta. And it's the locus where z mu of zeta, so this is for mu and gamma. Z mu of zeta divided by, z mu is a function of u, divided by zeta is real. So I mean, as we saw already in the, when we were talking about field theory, without any defect, z gamma of u over zeta. It's the locus where z gamma, z mu. So before we had a picture of the Coulomb branch, and I said, well, you have a nice description of the physics everywhere except at some bad points. That's what Seiberg and Witten discovered. So there's no reason that can't happen. You have an infrared description which works in most places but doesn't quite work everywhere. Something goes wrong. What goes wrong is that some particle becomes massless, becomes lighter and lighter until it, okay. Anyway, something can go wrong. And what we're now finding is that if we ask a more refined question, if we ask also the question, I don't want to describe just the physics of the bulk theory, but I also want to describe the physics with this line defect in, then you can still find a nice, simple infrared description, but the breakdown locus becomes much more complicated. So there's this new structure that appears on the Hitchin base, which is these lines where something bad is happening. And the structure of those lines, it'll lead to some complicated kind of network on the Hitchin base. So this is a structure I kind of want to advertise on the Hitchin base. Codimension 1. Did I write dimension 1? Codimension 1. Yeah, no, this is one real equation, right? Now, it doesn't have to break down on this whole locus. Like here, I drew the locus where it actually breaks down in some example. OK, fine. So
So I've seen talks of it before that draw networks that look like that somewhere else.
yes, hopefully in the next talk we'll draw those other networks.
Okay.
They occur for essentially.
The same network, or
It's not the same network, but the physical story is always the same. It's always the breakdown of some infrared description. So that's kind of why I'm trying to. That's the unifying principle. OK. So by the way, maybe it's worth saying, I'll just say in words, what it means. Why does it happen that the thing breaks down? It sounds bizarre. In fact, what's happening is that this line defect is becoming extremely big when you go close to this wall. What does it mean for it to become big? So in the original high energy theory, you just put this defect here. Now, it may happen that, depending on parameters, what may happen is that this line defect will attract some particles of the theory. And there may be kind of stable configurations where the particle sits a long, long way away from the defect. There's some radius like this. Suppose I have an object like this. I can still describe it as a line defect, provided that I look at energy scales that are so small that this distance still looks small. But now imagine that it happens that as I change parameters, this distance goes to infinity. In that limit, there's just no good way of describing the thing without also talking about this particle. I can't describe it as just a thing in pure abelian gauge theory. And that's what happens at these walls. So you could describe the thing if you included this particle in your description. But I insisted on not doing that. I insisted on only using abelian gauge theory. And in that case, these walls are just there. OK, so what's the mathematical consequence of that? The mathematical consequence of that is that these integers, omega of p r gamma mu zeta, are only piecewise constant. So they can jump at these walls.
What's the dependence on R?
Sorry, R. Shoot, I've got R for two different things. This is the representation in which we're. Yeah, thank you. They don't depend on that other parameter. In fact, I mean, this is not even the compactified theory. There was no radius here. This is still all in the four-dimensional theory. OK, great. So now I want to use this to compute these functions.
I'm lost in the notation.
Yeah, sorry.
This badness condition, is it a condition just on the spectral curve, or is it a condition that knows the ambient situation?
It's a condition. So this condition is just a condition on the spectral curve. Now,
Like some of the periods are real? I mean,
yeah, exactly. Or that their phase is equal to zeta. That's right. It's just a kind of reality condition on the periods. Now, in order to calculate, this is sort of the locus where jumps potentially could occur. To calculate what jump actually occurs, for that I have to know, which line defect I'm looking at and which representation, all that stuff. But just to draw the potential jumping locus, all you need is the periods of the spectral curve. OK, so what we're going to do now, I guess I'll just write the sort of I'll just write the equation. We'll pick up next time. So what I was interested in, I mean, what I just said is really what I should be interested in. That's some categorical statement. But because I'm not good at the category, I want to do something that I can understand. So let's think about these functions. So let's compactify on the circle. Then we get an equation that says that the function, now this trace of a holonomial, this function, is going to be expanded as a sum over these gammas, these electromagnetic charges, expanded in terms of somehow simpler functions. It's going to be expanded in terms of functions which I call x gamma of zeta. So before I had a decomposition in terms of line defects in 4 dimensions. Now I'm compactifying that. We're computing the expectation values on the circle. And I'm saying the expectation value on the circle also gets expanded in terms of some functions. And what are the properties that these functions are supposed to have? OK, so the first property, the sort of 0th property, which is that they're multiplicative. So that's a property that comes from the operator product of the abelian defects. There's some tricky sign, which please don't ask me about. So then, how are they related to the simple formulas that we wrote before? So this function x gamma of zeta, it can't be just equal to the simple formula I wrote before. You'll see why in a second. But it is asymptotically equal to that. So and it's asymptotically equal in two different senses. One is, so now we're really compactifying on a circle of radius r. So I do have this r here. So x gamma sf, this is this thing I wrote before, exponential of r z gamma over zeta plus I theta gamma plus r z bar gamma zeta. I guess I'm looking at the Hitchin real section. I said I would only look at the Hitchin real section, so then this will be gone, actually. And we'll just have this. So these functions are not equal to that, but as r goes to infinity, we're going back to the limit, the real infrared limit of the four-dimensional theory. We're making no modification to the four-dimensional theory. So in that limit, we go back to this simple formula. Another thing, which is a little less obvious, or even less obvious, is that you also get this kind of nice asymptotic behavior as zeta goes to 0 or infinity. That's somehow morally because as zeta goes to 0 or infinity, we're going to this topological limit. We're going to the supercharge, which was relevant for Donaldson theory. And in Donaldson theory, everything is topological. It doesn't depend on r. So what was true in the limit as r goes to infinity should be also true in the limit where I go to Donaldson theory. So far, this is all consistent with just saying that x equals x semi-flat, which would be pretty nice. So the very last thing that I'll say is the last condition that these things are supposed to have has to do with these walls. So we have these walls. And notice at the walls, it looks like something funny is happening. This function is a perfectly smooth function on the Hitchin moduli space. By definition, it was manifestly a smooth thing. On the other hand, I just told you that these numbers are going to jump as we move around from one IR description to another. So in order for those two things to be true, these functions have to also have a jump. And knowing how this jumps exactly tells you what the compensating jump of this has to be. So I'll just write that formula. So as zeta and u, as the parameters cross this line that we called L mu, or this wall that we called L mu, we have this collection of functions. It jumps, and it jumps by, but you can work out exactly what the form of the jump is. Maybe I'll say a few words about how you do that next time. But anyway, here's what the form of the jump is. So the function just gets multiplied by some explicit kind of product involving some other x's. The x is x mu. This wall was labeled by a charge mu. And there are some integers that appear here. So some funny product like this, where these integers, so these integers are also dimensions of some Hilbert space, not the same Hilbert space. For the moment, let me just say there's some computable numbers. So these you can really get. And so these conditions that I told you, properties 0, 1, 2, and 3, are actually enough to completely pin down these functions. So 0, 1, 2, 3 determine these functions x gamma of zeta. And so they also determine the functions that I was originally after, these traces. I'll just call them f. F of zeta. So this is the kind of computational scheme for learning something new about the Hitchin space. I mean, knowing these functions, as it turns out, knowing these functions is equivalent to knowing the whole hyperkähler metric, because these are kind of Darboux coordinates for the holomorphic symplectic form. So knowing these coordinates, if you can compute these functions in an explicit way, you can compute the whole hyperkähler metric. Yeah.
The integers omega, were they determined?
These integers?
You said they existed, but
yeah, so there's a recipe for determining them in any particular example. Now, in order to, yeah, so right, so there's kind of two steps to this thing. So one step is to determine these functions x gamma. To determine those, I actually don't need to know these coefficients. I only need these coefficients when I want to reassemble them into the UV things. But I do need to know these other omegas. Yeah, so sorry, there's two omegas here. There's the omega that's just omega, and there's the omega with these bars above and below it. This is called the framed. These are so-called framed BPS states, and so you put this frame around the omega. These are the so-called unframed BPS states. They're both dimensions of Hilbert spaces. One of them was the dimension of a Hilbert space with this defect inserted. That was how I described it. This is the dimension of a Hilbert space without any defect. So they're both Hilbert spaces attached to the theory, just slightly different Hilbert spaces.
Okay, so those both sets of numbers can be determined?
Yeah, in any particular example, I guess I'll show you how to do one next time. In any particular example, you can determine both sets of numbers. They turn out to have a nice concrete geometric meaning. Yeah, so, okay, so I mean, that's some relatively detailed thing, but the qualitative message is just that, this map from the ultraviolet to the infrared is a very powerful map. It should be used sort of for everything. So, I mean, Tudor also was using this in his description of, he was using essentially the same thing. He had some boundary conditions we described in the UV. He was looking at what they look like in the IR. I think a lot of the most powerful applications of quantum field theory all come down to using the same trick. So, okay, so I advertised this trick. Thanks.
Which one was UV and which one was IR?
Oh, the UV was the sort of fundamental description of the thing in terms of paths on the curve C, and then I said that when I went to low energies, I described it in terms of abelian gauge theory. That abelian gauge theory had to do with the covering.
So am I right that the F is the UV and this?
Yes, absolutely. The F is yeah, that's right. This is the UV function, and you're computing that function by expanding it in terms of these IR functions. Or at the categorical level, you have some line defect, and you're expanding it in terms of objects of some simpler category.
And what is the fact about physics that lets you make that computation in the IR?
The fact about physics, okay, so I guess there's two facts, right? So one fact is, one fact is that we know, thanks to Seiberger-Witten, we know exactly what the infrared description of the theory actually is. And the other fact, which I didn't fully explain, is that these line defects in the UV actually do have a good infrared description. So a priori, it was possible that they just had no good infrared description. Now, why did it work? I don't think I have a fundamental explanation of why it worked so well.
Like at some point, you need to say the words non-renormalization theorem, because otherwise these two things might vary by some constant.
They might have differed by. I'm not completely sure why it works so well. I agree with you that sort of a priori, you might have been surprised that this equation would hold on the nose. You might have thought that there would be corrections to this x gamma of zeta, which would be different for every different UV line operator that you tried to decompose. I think what's clear is that you'll have some expansion like this for each UV line operator.
So
and
expansion like asymptotically, not even inequality.
Well, so again, there are sort of two assumptions. So one assumption is that this UV defect has any IR description at all.
What does that statement mean? That has an IR description?
Yeah, it means that if you compute any correlation function in the presence of the UV defect, so okay, let's first remember what it meant for local operators to have an IR description. What that meant was that when we compute any correlation function of the full original UV field theory, that it's approximately equal to some correlation function of the simpler IR theory. And what approximately meant in that case was something precise. It meant that if you look at the low Fourier modes, if you expand the thing in a Fourier expansion, look at just the low Fourier modes, that it would agree up to corrections of a certain order. Now, I could say exactly the same thing in the presence of the line defects. A very similar thing that they agree at low energies, and what that means is that correlation functions with these things inserted agree up to corrections. And the question is why are those corrections absent in this case? Right. So I didn't write. there are some corrections here because this function is not the original function x gamma semi-flat. The question is, why are the corrections the same for every different UV operator that you choose? I think that's the question. And I agree, actually, I don't know why it works so well. So there's a little bit of magic going into this, which is not, it has the flavor of topological field theory more than of.
So why do we think it's true? Like based on what evidence?
Oh, because it works very well. So
Like we can give both sides in some examples.
yeah, in many examples. So right. No, you're right. So you sort of have the idea to do this, and then you go away and you check it, and it works.
There's not derivation from physics of this equation.
I mean, yeah, I think by high standards that's right. I mean, there are a lot of things that are done in physics where you sort of believe that there's probably some non-normalization theorem that's helping you, but you don't always prove it.
But if you had such a theorem, then that would be.
No, that's right. That's right. No, you can certainly imagine. No. You can easily imagine somehow proving that this thing doesn't receive any corrections. Yeah. No. So you can imagine such a derivation, but I don't. No. I think you're right to be cautious. So I told you that it's something about the UV to IR flow. It is something about the UV to IR flow, but it's in the same way as like the relation between Donaldson and Seiberg-Witten. So the fact that that works exactly, in that case, has to do with the fact that the thing you compute is topological. The fact that that works on the nodes. And here too, this thing has some kind of topological spirit to it, which is making it work. Yeah, and I'm not claiming to know exactly why.
So the Hitchin space and the other complex structures, it's an algebraic variety in two different ways.
Yes.
Is that?
Yeah, I mean, you don't use nothing I said. You sort of use the algebraic structure. It's true that these functions are going to be algebraic functions in the Betty structure, the one where it's representations of the fundamental group. But the fact that they're algebraic in that structure somehow didn't play any role in.
You said they made a basis for A1.
No, a basis, just like a linear basis. A basis for the. Oh, I see. You're saying that's really like the ring of the basis for the algebra of all algebraic functions. Well, that's certainly true, at least. Does the physics know about algebraic functions? That's a good question. I mean, it's true that they're algebraic, and it's true even that the process of actually producing these functions, so maybe I'll show you next time, in the process of actually producing these functions, you do wind up sort of solving algebraic equations. I mean, but I mean,
Kevin's talks had Betty and Durham in them. I mean, so that point of view certainly has a Betty version and a Durham version. He talked about the right-hand side being Durham versus, but not Betty in his examples, but you could also have a Betty right-hand side.
Yeah, so I don't see that very clearly. I mean, in the language of the, I mean, maybe this is related to the fact that I said there's something topological going on that I don't understand. But certainly in the language of the physical theory, you don't feel that at all. I mean, it's just this hyperkähler space, and you couldn't care less about its algebraic structure.
But you only compute polynomial things with these x's, right? You only compute.
Oh, you mean, well, it happens that the line defect, right, I mean, it happens that these vacuum expectation values of line defects, right, they just are functions of the holonomies, and so those are, algebraic in one of those structures. And then you're right, then they're algebraically related to these x's. I mean, all those things are true, but I don't know sort of why they don't fit into some general world where like, oh, it had to be algebraic, as far as I know.
Maybe a dumb question. I don't. In the first condition on the chi's, I'm not sure I understand what the bracket. Parenthesis. Is that just a constant that you've omitted to name, or?
Here.
Yeah. There.
-1. Yeah.
Could you say more about why the IR description of the theory is this a billion super angles on the spectral curve? Before I think the spectral curve just came up as a deformation of these like multiple brains on a single guy, which got formed in some way.
Right. No, I didn't say, I didn't mean to say, and I hope I didn't say that it was Yang-Mills on the spectral curve. I just meant to say that the spectral curve enters into the description of, for example, the charge lattice and the periods and so on. I didn't mean to say that that you obtain a 4-dimensional field theory living on the spectral curve. There is a sense in which it could be described morally as the 6-dimensional theory living on this spectral curve. So that's true. So I'll say it just as a moral statement. So you know, we're starting with the 6D theory on this curve here, but if you think of it in terms of the M5 brane, so you have to go back to the M theory description for this. What you have is a thing that's wrapped on k copies of this curve, and then you say going out on the Coulomb branch is like a deformation of that, where you replace that. Those k branes get replaced by one. By now, this is like a non-reduced thing, and in that linear system, there's another thing which is just this reduced thing. Well, there could be other kind of singular. No, but I mean that's what the Hitchin base is. The Hitchin base is exactly the moduli space of covers of this thing. So all those points are in there. So yeah, so you could indeed say that what you're studying is the 6-dimensional theory, but now the abelian version of it on this curve rather than this one. Exactly, exactly. So yeah, when you have like k branes sort of all sitting together, that's the non-abelian version, and when you separate them out, then it's the abelian one.
And why is that the same as going to the IR?
Well, this is the okay. So two things. So here, what I'm describing here is the moduli space of that quantum field theory. So it's so the moduli space is always kind of an IR. So I mean, to say the moduli space, that's always related to the IR. Maybe I don't want to say more than that.
But there's some claim you're making, which is that the IR description of this theory is on the right-hand side. You're doing all this computations in the abelian here.
Yeah, that's right.
So what is the statement we're making? Like, why is that correct?
So I mean that really goes back to yeah. So when you have one M5 brane, yeah, it doesn't quite have a Lagrangian, but nevertheless you can describe it. You can work out what its dimensional reduction will be. So just literally take one M5 brane on this Riemann surface, just a single M5 brane. Then you can calculate in purely Lagrangian terms, despite the fact that strictly speaking it has this self-duality problem. You can really work out in just Lagrangian terms what the 4-dimensional thing will be, and you really get an abelian gauge theory. The other answer is that that's what Seiberg and Witten told you to expect in general, but in this case you can see it directly from that. Yeah. Okay, I hope we're done with that.